Welcome, and thank you for joining us today. In this session, we'll share with you how Amazon Redshift makes it easy to connect to all your data sources and how you can start analyzing your data, not only just exploration, observation, but also running prediction using SQL. I'm Harshita Patel, a principal specialist SA at AWS. Joining me today is Anusha Challa, senior specialist SA at AWS. We'll get started by sharing how customers are becoming data-driven, how they are evolving their data platform, how Amazon Redshift is enabling their data-driven journey, followed by a hands-on demo, and we'll also share with you common patterns that we have observed and worked with customers across different verticals. Customers are becoming data-driven. They are evolving their data platform to drive their business. They start off their journey with dashboarding and reporting. They're integrating their data across data sources, data lake, databases, data warehouse. They're also tapping into near real-time data and running prediction on that near real-time data. Further, they're monetizing this data as well as sharing this data for collaboration using data mesh patterns. And they're completely reinventing their business using generative AI. As the customers are evolving their data platform as well as becoming data-driven, they are also marching towards a modern data strategy where they are unifying the data across different data sources, providing security, and providing access to this data to the end users to make data-driven decisions on time. They are modernizing their technology stack, which allows them the scale, the performance, price performance to handle this growing volume and complexity of the business use cases. They are also introducing machine learning in their data pipeline and completely reinventing their business. With this modern data strategy, customers are also adopting modern data architecture, which provides them the ability to collect data across different data sources in different forms, coming at different frequency, at volume, and at scale. Data could be streaming, coming into the data lake. Data is also coming through the transactional source system. This data is used for analytics, reporting, dashboarding. Providing governance and fine-grained access control, this data is opened up for access to the end users for analytics. This data is also used for machine learning to train the models. For example, to personalize customer experience. And based on customer, what they selected, based on the promotions they did, what are their likes, what products did they select, all of this is feedback back as a data source, which is then further used to fine-tune the machine learning models. So the flow of the data is through this loop, data loop, which integrates different services. For example, data lake or concepts, data lakes, databases, data warehouses, machine learning. With the modern data architecture on AWS, it allows to break the data silos. At the core of it is data lake. All the purpose-built database services or the services which allows scalability, performance, they're fully managed service which provides price performance or they're cost effective. At the heart is Amazon S3, the data lake, using AWS Lake Formation for governance and access control, using Amazon SageMaker for machine learning, using Amazon Aurora as relational database, Amazon EMR for big data processing, and in order to perform analytics at scale, using Amazon Redshift using simple SQL. Amazon Redshift is a fully managed data warehousing service. It allows you to integrate and collect data from a variety of different data sources. And you can democratize access on this data, provide access to your end users to run analytics using simple SQL. It allows you to handle your growing data at scale, provide you the performance, or whether your workload complexity is increasing or end user base is increasing at price performance. It has built-in security at no additional cost. And with Amazon Redshift serverless, it is completely simplifying the end user experience, which is used for self-service analytics. To connect to Amazon Redshift, you can connect using JDBC, ODBC driver. You can use products of your choice to run the analytics on top of the data in Amazon Redshift. You can also use Data API for programmatic access. And as we looked at the modern data architecture, it's not only just a particular service, but it also allows you to extend your data warehouse to the data on the data lake in any open formats. It also supports transactional table formats, Hudi, Delta Lake, Iceberg. So you as an end user have the ability to run analytics or join the data which is in your data lake to the data on Amazon Redshift. The recent announcement of autocopy, which completely simplifies the ingestion of the data on S3 without having to build data pipeline. With integration with Amazon SageMaker, this allows the capability using SQL to create, train, and deploy a model for prediction. You can do local inference on Amazon Redshift. You also have the ability to do remote inference. Integration with Apache Spark. Apache Spark Redshift connectors are integrated and available with AWS Glue, as well as Amazon EMR, which allows you to build advanced analytics data pipeline leveraging the data on Amazon Redshift. For real-time analytics or near real-time analytics, deep integration with Amazon Kinesis data stream, Amazon Managed Streaming for Apache Kafka, simplifying the pipeline and running the analytics from within Redshift using SQL. To tap into the operational data store right from within your data warehouse, Amazon Redshift, is the integration with Amazon Aurora or Amazon RDS MySQL in Postgres using the federated query. And to take it a step forward is the introduction of zero-ETL integration, starting off with Amazon Aurora MySQL, where as and when the changes are made on your operational data store, those are replicated to Amazon Redshift in near real time. So from an end user perspective, they're connecting to Amazon Redshift. The data could be coming from the data lake or from the operational data stores, or the data is getting ingested in batches, mini batches, or near real time. So Amazon Redshift provides that unified, simplified view. And to further, for workload isolation, collaboration, monetization, the ability to share the data securely to other Amazon Redshift data warehouses without having the need to duplicate the data. The feature is data sharing. So with Amazon Redshift, it allows you to run analytics at scale on all your data. And also, using the simple language SQL for analytics, you can provide access to your end users, your decision makers, and they can integrate the products of their choice using JDBC or ODBC drivers. I'll now like to hand over to Anusha to walk us through the demo.
Thanks, Harshita. Like Harshita mentioned, it's important to be able to connect to all your data and perform analytics using tools and services that are well suited for your use case. We'll see a demo on how Amazon Redshift enables you to achieve that through a realistic use case. Example Corp is a retail firm, and they get data from a variety of sources, like how most of you do. Their transactional customer and product data is in an operational database. Their credit card payments are streamed as JSONs, and their web server loads log files continuously into the data lake. Example Corp wants to ingest transform, analyze, and run visualizations on all of this data. They also want to run predictions to identify fraud in their credit card payments. Let's see the architecture that solves this use case, and this is that architecture. To the left, all their data sources are present. Data from all these sources is ingested into Redshift through easy to use direct and seamless integrations. All these integrations are zero-ETL solutions, which means they're simple to use, set up, and monitor. We'll take a look at each of them as we progress. To the right are use case specific analytics solutions that integrate directly with Redshift for a variety of analytics use cases. Data can be analyzed at scale to achieve business outcomes through direct integrations available with each of the services mentioned here. We'll take a deeper look at each of these integrations as we progress. The core of this architecture is Amazon Redshift. Redshift is deployed in a hub and spoke architecture with two separate endpoints. One endpoint is used for ingestion and transformation, and the other is used for consumption workload. By separating workloads like this, example card can achieve complete workload isolation. Let's start diving deep now. We'll start with ingestion. The first data source we will integrate with Redshift is the transactional customer and product data from Aurora MySQL database. Operational databases are one of the most common sources of data into the data warehouse. Where direct integration is not available, you would need to replicate data using third-party or AWS replication solutions, or build and maintain complex and cumbersome ETL pipelines. Even by doing all of that, achieving near real-time latency can be challenging. To avoid this heavy lifting, AWS offers a direct zero-ETL integration from native operational database service Aurora MySQL to Redshift. This integration is scalable, reliable, and cost-efficient. Within seconds of transactional data being written into Aurora MySQL, it is made available in Redshift so that you don't have to build and maintain the complex data pipelines. You can integrate multiple Aurora database clusters with Redshift, thereby consolidating them for insights across all of your operational data. This integration enables you to leverage Redshift's analytics capabilities on your operational data through seamless integrations. Let's see a demo on how this customer and product data from Aurora MySQL is integrated with Redshift in near real time. What you're seeing is Amazon RDS Management Console, and the database that has customer and product information is this particular database. Let's take a quick look at the contents of this database. It's a MySQL database, so I'll be using a console to connect to the MySQL database. This is the database that has the customer and product information, and here are the two tables within that database, which are customer and product. Now let's see how we can integrate this data with Redshift using a zero-ETL integration. For that, let's go back to the RDS console and then click on zero-ETL integration. The first step is to create a zero-ETL integration. We'll go ahead and give this integration a name, and then we will choose the source database from which you want to create the integration from, and then you choose the target into which you want to load this data into. This is a target Redshift namespace. Once those selections are made, you can go ahead and click Create Zero-ETL Integration. I've pre-created this integration, so I'll go ahead and cancel this. Depending on the amount of data you have, this ETL integration could take some time to be created. Once it is created, you can see the status is active. And this is the ETL integration that we're going to use. You can see the source and the target Redshift namespace out here. To access this integration from Redshift, we will go to Redshift Query Editor v2. This is a simple web-based interface to access Redshift. You can view the integrations that are available for Redshift by querying SVV integration table. I'll go ahead and run this query. Here you can see the list of integrations that are available. If there are multiple integrations from multiple Aurora databases to this Redshift endpoint, you would be able to see all those integrations here. When you look at the integration, the next step that you would do is create a database for that integration. So you just say create database, give this database a name, from integration, the integration ID that you have seen previously here. Once the database is created, you would be able to see it just like any other database here. I would go ahead and expand it. You can see the schemas that are available, and within the schemas, you see the two tables are available. The two tables, customer and product, that we have seen in the MySQL database are available here. At this state, you can run any queries on these tables. So as a first step, I would go ahead and count the number of products and the number of customers from this data set. I'll go ahead and run that query. And you can see there are 99 products and around 500,000 customers in this specific data set. If I go ahead and make changes in my SQL database, you would see them reflected here. Let's go ahead and see that. I'll go back to my SQL database, and then I will insert a product number 100 into the database. And this product number 100, it's a comforter product, and the description is winter comforter. And I have inserted this 100th product into the database. Now this product should be reflected in Redshift. To verify that, we'll go to editor. Now you see 99 products. Let's run this query again to see if the product number 100 is reflected. And as you can see, you now see 100 products. Similarly, you can make updates in the MySQL database and you can see them reflected in Redshift. Let's go ahead and perform an update. I have updated product number 100 and I've updated the description to updated winter comforter. That's the new description. This has affected one row and you would be able to see this change reflected in Redshift. Let's go back and verify that. I'll go back to Redshift Query Editor V2 and then take a look at product ID 100. I'll quickly go ahead and run that. And you can see the description updated winter comforter reflected here just within few seconds of it being made in the MySQL database. In this way, all the updates that you make in the MySQL database are reflected in near real time within few seconds in Redshift so that you can run large-scale analytics on top of your Aurora data. Next source is streaming payment transactions. To load data from stream into the Redshift, we will use streaming ingestion feature in Redshift. This feature is a native integration between Amazon streaming services, Amazon Kinesis data streams, or Amazon managed streaming for Apache Kafka. You can ingest hundreds of megabytes of data per second, query the data in near real time, and drive your businesses forward with analytics. This is also a zero-ETL approach and can be established within just 2 steps. When loading data from the stream to Redshift, you can choose to define a schema or ingest the semi-structured data as is with super data type. In this demo, I'll show how credit card payment transactions from Kinesis data streams are loaded into Redshift within seconds. The same can be done using Amazon managed streaming Kafka as well. Let's dive into this demo using Kinesis data streams. What you're seeing is Amazon Kinesis Management Console. And the stream that we would be using is the customer payment transaction stream info. Payment transactions, the credit card payment transactions, are being loaded into this particular stream as we speak. Let's see how data from this stream can be integrated with Redshift just within few simple steps. We'll go to Redshift Query Editor V2. The first step to integrate the stream with Redshift is to create an external schema from Kinesis. You can use MSK as well here. This external schema acts as a connection between Redshift and Kinesis. Once this external schema is created, you can go ahead and create materialized views using just the external schema dot the stream name notation. Using this notation, you can access any Kinesis stream that the IAM role has access to. Using this notation, we'll go ahead and create a materialized view. And in the materialized view, we're materializing the entire payload from Kinesis as is in super data type. And this materialized view is set to auto refresh yes, which means that any new data that is in stream will be automatically loaded into Redshift in near real time within few seconds. I've pre-created this materialized view, and at this time, data from the stream is automatically being loaded into Redshift as we speak. Let's go ahead and check the status of that. To check the progress, we'll get the count of records from the materialized view and the freshness of the data. I'll go ahead and run this. And you can see that the count is 68,700 and it is refreshed last just 9 seconds back. I'll go ahead and click run again. You'll see the count increase and the freshness updated. I'll go ahead and click run again. And you can see the count has increased and the freshness has been updated. I'll go ahead and click run again, and you see that the count would continue to increase and the freshness will continue to update, and it is just few seconds from the time data is produced on the stream. At this point, you can query the materialized view to access the data. You go ahead and query the materialized view, and here is the data in the materialized view. And you can see the entire payload represented in the payload field here. And this is the payload field. It is unstructured data. Sorry, it is semi-structured data. Within the semi-structured data, you can see the attributes that are available within the payload. Now, you can access individual attributes from this payload using particle, using simple dot notation. Here is a query that gets individual attributes from the payload using particle. I'll go ahead and run this. And this query is just getting from the view, from payload field, the individual attributes and showing the data for you. It's this simple to extract individual attributes out of your semi-structured data. This integration seamlessly supports evolving schema use cases. Your schema might change tomorrow. You may add new field, you may remove existing fields. While you're selecting attributes, if that attribute exists, you'll get the data for that attribute. If the attribute doesn't exist, you would see a null. This way, this integration seamlessly supports evolving schema use cases and enables you to perform large-scale analytics on your semi-structured data sets. You have the ability to store individual attributes while you're creating the materialized view itself. You can choose to do so if your use case requires that specific feature. The next source is continuously ingested weblog files into Amazon S3. To load these files into Redshift as soon as they're created in Amazon S3, we will use autocopy from S3 feature, which is a direct integration between S3 and Redshift. This integration simplifies data loading from S3 into Redshift significantly. Before this integration was available, loading data from S3 into Redshift in near real-time fashion required complex pipelines to identify new files and then load them. Avoiding all that heavy lifting, this integration tracks your Amazon S3 path and automatically loads new files without the need for additional tools or custom solutions. Amazon Redshift customers typically run copy statements to load data into their tables. To use this integration, all you need to do is to store these familiar copy statements into a new construct that we have introduced. It's called the copy job. The copy job automatically loads the new files detected in specific Amazon S3 path while excluding previously loaded files from the ingestion process. Now let's see a demo for that. The weblog data path is the one that is getting log files data and they're getting loaded into 2023 folder. Let's see how many files are there. There are 510 files currently in this path. Let's go back and get the count one more time for this path and see if files are being continuously ingested. As you can see, now there are 514 files, indicating that data is continuously being loaded into this weblog data folder. The data is nothing but weblogs. To integrate this path into Redshift, we can create a near real-time ETL integration pipeline to load the newly incoming files from this path into Redshift in near real time within few seconds. Let's see how it's done. Data from that path will be loaded into this table called weblog data. Let's go ahead and run this SQL, and you can see that there are no rows in this table right now. In order to create an integration from the S3 path into this table, we will use the familiar copy command, which copies from a specific S3 path using an IAM role. And to that, we will add a clause saying create a copy job, give that copy job a name, and we will set it to auto, indicating any new data that is created in S3 should be automatically loaded into this table. Let's go ahead and create this copy job. When the copy job is ready, at this point, data from S3 should have automatically been started to load into Redshift as we speak. In order to check the status of that, you can use system tables and query for the copy job ID that we've just created. And go ahead and run this. And you can see the job status here. There are X number of loaded rows, and the source file count can be seen. Now, when I go ahead and click run for this SQL sentence again, you will see the number of source files increase, indicating that the new files are being continuously loaded into this table, and the loaded rows also has increased. At this point, you can run analytics on this data using simple SQL statements. I want to count the total web registrations by year and also get the total number of web registrations altogether. For that, I will use the analytics function cube. It is one of the grouping functions that is available in Redshift. There are many other grouping functions that are available like this. The output is total web registrations by year and the overall total web registrations that example call received. So with this, in just few simple steps, we have set up a near real-time integration pipeline from Amazon S3 to Redshift, and data is being continuously loaded and insights are being generated, as you can see. Moving on. Next is data transformation. If you choose to apply transformations on the ingested data, let's see how that can be done. For data transformation, we will use AWS Glue. Glue is serverless data transformation service. Redshift integrates directly with AWS Glue, enabling you to apply transformations on your data seamlessly. Glue provides an easy-to-use interactive visual ETL interface that makes it easy to create, run, and monitor ETL. The visual interface allows you to compose data transformation workloads using something called nodes. You'll see what nodes are in just a while. Each node represents a data handling step. These nodes are later converted by Glue into code and they're executed. To transform data, we'll use AWS Glue. This is AWS Glue's management console. The first step is to create a data connection. For that, I'll go to Data Connections, and then I'll click on Create Connection. I'll give this connection a name, and then choose the connection type as Amazon Redshift. When you choose that connection type, you can see the list of Redshift endpoints that are available to you pre-populated. Pick the Redshift endpoint you want to connect to. Give the database details such as the database name, the database user, and the database password. Once those are done, click Create Connection. This will create the Glue Redshift connection. Using this connection, you can now author ETL jobs. You can do that using Visual ETL, which is easy to use interface. Go to Visual ETL and then choose the visual blank canvas and then click on Create. You can see that you can add sources, transformations, targets to this ETL job. Right now, this is a blank canvas. To this canvas, we'll be adding nodes, which would define the end-to-end ETL pipeline. The first step is to add a source node. I want to add Amazon Redshift as a source. I click on that, and you can see that the source node gets automatically added. Now let's configure this node. Choose the Redshift connection we just created. I'll go ahead and choose that connection, and you can see the schemas pre-populated for you. I'll choose the public schema, and in this ETL job, I would like to aggregate log file, the log data that is being loaded from Amazon S3 into Redshift using autocopy from S3. So I'll choose the table into which the log files are being loaded, which is weblog data. I've chosen the schema, I've chosen the table. And at this time, I'll go ahead and give this node a name. I just call it logs. With this, the source configuration is complete. Now to this ETL pipeline, let's go ahead and add a transformation. I want to perform aggregation of logs. So when I click aggregate transformation, you can see that the aggregate node automatically gets added. I'll click on this and go ahead and configure it. For aggregation, I will choose the fields that I want to aggregate by. I want to aggregate by web page and by the application. I've chosen web page and application fields as the group by fields. And then I'll go ahead and perform the aggregation. I want to do a count distinct on the IP addresses. I've made my selections. With that, configuring aggregate transformation is complete. Now finally, I want to load this aggregated data into a target. So for that, I go to the data tab here, and then I would choose targets. And within targets, I can choose Amazon Redshift target, and you see that Amazon Redshift is automatically added to the target here. Let's configure this target. We'll pick the same connection that we have created before, choose the schema into which the data should go into. I'll choose the public schema, and then choose a table name. I would call this aggregated log data table. There are different ways in which you can load data to the target table. You can append if the table already exists. You can perform a merge. You can do a truncate and load, or you can drop and recreate. The table that I'm going to create does not already exist, so I'm going to drop and recreate the table. With that, configuring target is complete. At this time, I'd go ahead to the script and job details, and then give the script a name. I'll call it aggregate logs. I'll also verify the other job properties such as number of retries, the job timeout, so on and forth. Everything looks good. At this time, I'll go ahead and choose the IAM role to execute this job and then click Save. With this, the job has been successfully saved. And to execute the job, I'll just click Run. In the backend, Glue converts the visual ETL code into actual executable Python code, executes the ETL, and stores the results. With just these simple steps, you can transform your data using visual ETL in Glue. Next is machine learning. One of the example Corp's objective is to predict payment fraud using ML. Let's see how to achieve that. For machine learning, we will use Amazon Redshift ML feature. It is a direct integration between Redshift and the fully managed machine learning service, Amazon SageMaker. Amazon Redshift ML democratized ML to all personas. It enables your data analysts and database developers who typically only have SQL skills to benefit from ML. They can create, train, and apply machine learning models without learning new tools or languages. Before this integration, you had to export data to S3 and use SageMaker to create models. With this integration, all that heavy lifting is eliminated. Let's see a demo on how simple it is to do ML with Redshift ML. When you want to use machine learning, the first step is to identify historical data to train that machine learning model. Example Corp has customer payment transaction history in this table called customer payment transaction history. Let's quickly go ahead and query that table. This is the historical data that is out there. This historical data has a history of transactions that are made towards Example Corp, and it has a field called transaction underscore fraud, which is a binary field 0 or 1. 0 indicates that there is no fraud. 1 indicates that there is a fraud within the transaction that is made. Because Example Corp wants to predict fraud in credit card payments, they will use this data set as a training data set to create a machine learning model. Let's see how they would do that. To create a model out of that data set, example corp would just use a simple create model statement. To this model statement, they will pass a select statement as an input, and the select statement would select the important fields from the data set that are crucial to detect whether the payment resulted in a fraud or not. They would indicate that transaction underscore fraud is the target field that they're trying to predict. Once this model is created, a function will be made available to them with the name function underscore customer underscore cc underscore fraud. To this model statement, they would pass an IAM role with necessary permissions to access SageMaker and the underlying S3 bucket into which intermediary datasets would be loaded. It's this simple to create a machine learning model. As you can see, they haven't specified any model type or any other machine learning model attributes, which means that auto machine learning, auto ML would be invoked to identify the right model that fits this data set. If this direct integration between Redshift and SageMaker is not available through AutoML, what you would typically need to do is pass this data set through a variety of models and identify the model that fits your data set right. Redshift and SageMaker integration alleviates this heavy lifting. Through this integration, this data set would be passed to hundreds of machine learning models. The right model is identified and it's imported into Redshift for inference purposes using simple SQL statements. This model has been pre-created, and let's check the status of that model. To do that, we'll run the show model statement. You can see that the model is ready, and Redshift ML automatically identified that this is a binary classification model and imported this model locally to perform predictions. To get the accuracy of this model, we'll compare the actual transaction underscore fraud label to the prediction that is generated by the model. I'll go ahead and run the SQL statement. And here is the result. You can see that this model has an accuracy of 91%. Finally, let's go and run predictions using this model. To run predictions, we will use the function that is made available by the model. To that function, we would pass the necessary attributes as inputs to generate a prediction. The inputs are passed from the customer payment transaction stream. This is a stream to which the credit card payments are continuously being streamed. So on the data that is being loaded on near real time, we would be running predictions to identify whether that credit card payment has resulted in a fraud or not. We'll go ahead and run the statement that would run predictions on the incoming data in near real time to generate outputs. As you can see, this is a simple select statement. And here is the output. For each credit card payment that is incoming, you can see a target field fraud underscore prediction, which is generated with a value of 0 or 1, 0 indicating that there is no fraud, 1 indicating that there is a fraud for this particular transaction. It is this simple to generate predictions in few simple steps using simple SQL statements using Redshift ML, which is a direct integration between Redshift and SageMaker. Next, let's look at data sharing. So far, we have used the first endpoint to perform data ingestion, transform the data, and use Redshift ML to run predictions. As a next step, we want to make this data available for consumption and host the consumption workload in a separate Redshift endpoint. Data can be shared between these endpoints using data sharing feature. Once we set up data sharing between these two endpoints, data produced by the first endpoint can be accessed seamlessly by the consuming endpoint with transactional consistency. You do not have to make any copies of data. Consumer uses its own compute to run queries and doesn't lay any burden on the producer's compute. In fact, the producer's compute may be paused and data sharing still happens. By separating the workload in this fashion, we can isolate the ETL and consumption workloads so that they don't interfere and impact each other. It also improves agility by allowing sizing endpoints independently and choosing them to be either provisioned or serverless based on the workload's requirements. Before diving into demo, let's take a look at some terminology. The terminology we use with respect to data sharing is producer and consumer. Producer is the endpoint that owns or creates the dataset, and consumer is the endpoint that accesses the dataset in place. Setting data sharing between Amazon Redshift endpoints is a two-step process. First step is performed on the producer endpoint, where the administrator creates a data share and adds object to that data share that they would like to share. The second step is on the consumer. In the consumer endpoint, we'll create a local database reference from the data share. And after doing that, consumer can access data from producer seamlessly and grant permissions to appropriate users and groups. For consumption purposes, we'll be using the consumption workgroup and the consumption namespace. Let's now see how to set up data sharing between the producer cluster and this consumer cluster so that the consumer can access the data as is in place from the producer cluster. For that, we'll go to Redshift Query Editor v2 and we'll start from the producer side. On the producer side, we will create a data share. So we'll first create a data share for the data that is replicated from Aurora MySQL. We'll go ahead and first run the statement to create the data share called consumption customer product. To this data share, we'll go ahead and add the schemas that we need and the tables that we need. So I'm going ahead and adding the schema customer product and all the tables, as in the table customer and product to this particular data share. The next step is to grant usage on this data share to the consuming namespace. We'll go ahead and run this. And this is the namespace ID of the consumer consumer namespace. We'll repeat the same steps for the other data sets that are coming from S3 using autocopy from S3 and streaming ingestion. So we'll go ahead and create a data share and call it payments and logs. This is the data that is coming from streaming ingestion and Amazon S3 through autocopy. To this data share, we'll add the schema that we need and the tables that we would like to add. I'm adding the weblog data and the customer payments stream data into this particular data share. And finally, I'll grant usage on this data share to the consuming namespace. With that, the setup required on the producer endpoint is complete. Now we'll go to the consumer endpoint. From the consumer side, you can see the data shares that are available to this endpoint. You can see both the data shares that we have created available here. On these data shares, we'll create a database reference, a local database reference to start accessing the data. For that, we'll use these two create database statements. These create database statements are accessing the data share that we've created of this producing namespace. The databases are now ready and created. Optionally, you can create an external schema pointing to the database reference that you have created and the specific schema so that you can avoid three-dot notation. Rather, you can access data using two-dot notation as shown here. I'll go ahead and run this create external schemas as well. The customer product schema is referring to the customer product schema from the customer product DB, and the public schema is referring to the payment logs DB's schema reference and the public schema. With that, the data sharing between producer and consumer is ready. You can go ahead and access data from the producer using this consumer endpoint using simple queries. You would access data from producer like how you would do any local table. I'll go ahead and run these queries that get the count of records from weblogs and the count of products. The weblog data is constantly refreshed, and the count that you see here is the constantly refreshed weblog count. And the product data is also constantly refreshed from MySQL database. Now, the data sharing is done. The consumer workload is ready. Let's go ahead and do data visualization. For data visualization, use Amazon QuickSight. It is a serverless BI reporting solution. It provides various visualization widgets to understand and visualize your data better. This is Quick Site Management Console. To establish a connection between QuickSight and Redshift, the first step is to create a dataset. Go to Dataset and create a new dataset. I'll choose Redshift as the data source type and give this data source a name. Choose a connection type. I'll choose the VPC using which I would like to make a connection and enter the database detail like the endpoint, the port number, the database name, the username, and the password for this specific connection. And then click Validate Connection. Once the connection is successfully validated, I can go ahead and create this data source. At this time in QuickSight, you can see the schemas within the database readily available. I can choose the schema that I would like to connect to. For example, to access the customer and product information that is being replicated from MySQL, I can go ahead and click Customer Product Table, choose the customer and product tables, and start visualizing them. Similarly, in order to view the payment logs information, I can go to the payment log schema and access the web log data readily here and start visualizing it. I've pre-created a data set. Let's go ahead and take a look at that data set. The data set I have pre-created is customer order payments. This data set already has the necessary information that is needed for the analysis that we are going to create. On this data set, I've created an analysis, and that is customer order payment analysis. This analysis is getting data in near real time from the sources that we have just integrated into Redshift. This analysis is powered by Redshift, and the data in Redshift is being refreshed from S3 automatically using autocopy from S3, from MySQL using zero-ETL integration, from the Kinesis data stream using streaming ingestion. And you can see many widgets created in this analysis to understand the data better. Once the analysis is created like this, using QuickSight to understand your data better, using a variety of widgets that QuickSight provides, you can go ahead and publish this into a dashboard. Let's see the dashboard into which it is published. This is the dashboard, for example, Corp's data analysis. You can see data published using a variety of widgets. The customer signups per year is a bar graph. There is a donut chart showing the revenue and the total revenue made by product. You can see a word cloud of the most selling products. You can see a map which shows the number of customers by postal code and the product that they're using. And you can see the count of product purchases for various products that are available. Like this, you can simply and quickly visualize data in Redshift using the direct integration available between QuickSight and Amazon Redshift. That concludes the demo. And in summary, we have seen a demo of data ingestion using various direct integrations. We have seen how operational databases can be integrated using zero-ETL integration. We saw how streaming data can be integrated using streaming ingestion, and saw how files from S3 can be continuously loaded into Redshift through autocopy from S3. We then saw how data can be transformed through a visual ETL interface in Glue, and how predictions on those data sets can be made using SageMaker. Then we moved on to isolate ingestion and consumption workloads using data sharing, and finally saw how data can be visualized using QuickSight, making this an end-to-end pipeline all the way from ingestion, transformation, running analytics to consumption. That concludes my demo. I'll hand it over to you, Harshida.
Thank you so much, Anusha, for such insightful demo. We'll now like to share with you common patterns that we have observed while working with customers across different industries, and how they are using and deploying those patterns using Amazon Redshift. The first is starting off with data sharing. For customers who are using Amazon Redshift Data Warehouse, both for their ingesting the data, transforming their data, as well as for consumption, they're looking at data sharing from a performance and price performance perspective to provide workload isolation. The concepts of Amazon Redshift Producer, which is the curator of the data, where the data gets written into. This data is shared securely to an Amazon Redshift data warehouse consumer. This could be a provisioned or serverless endpoint. And the end users are consuming the data directly from the consumer without having to change their pipeline using the simple SQL construct. When the consumer is running the analytics on the consumer, it's using the compute capacity of the consumer. To take it a step forward with workload isolation, customers are also looking for chargeback, where they have consumers based either on the specific of their workload or different departments or different teams. So in this example, there is one producer and n number of consumers. One could be for data science workload, one for dashboarding reporting, or the other could be for SQL client. This provides clear-cut chargebacks. Data sharing is available within account, across accounts, and across AWS regions. So customer, when they are starting the journey with a single account, they are looking at workload isolation. Customers where they have a centralized producer data warehouse, they not only have internal customers, but they could also have external customers where they are monetizing the data. They go with hub and spoke of federated model. For enterprises and organizations where there are multiple different teams or lines of businesses who are not only the data producers, but also the data owners, they are enabling, or data sharing is enabling them to adapt data mesh pattern with centralized governance. For customers who are monetizing their data or providing data as a service, where they are curating the data on a provisioned data warehouse, but they are securely sharing this data to the external clients using serverless endpoints. Customers are also integrating Amazon Redshift Data Share as a product with AWS Data Exchange to monetize their data. AWS Data Exchange completely simplifies the billing and the payment. And from a customer's perspective, when this data the product is available as Amazon Redshift Data Share, they can also integrate or consume this third-party data right directly within their data warehouse to enrich the data in the data warehouse. The second, more predominant pattern that we have seen is adoption of streaming ingestion, as well as running prediction on the incoming data. For example, working with customers in the gaming industry, as well as customers who are in the manufacturing industry, where the data is constantly getting ingested in near real time, and they need to get the insight as in when the data is arriving. So with the streaming sources, it could be IoT sensors, log data, but data could also be coming from Amazon DynamoDB streams. The integration with Amazon Kinesis data stream or Amazon managed streaming for Apache Kafka, the data is ingested into Amazon Redshift, materialized as a materialized view on Amazon Redshift, and then running analytics on top of it to generate near real-time insight. So to put this in context, the demo that Anusha did, the streaming data was the payment credit card transactions, which are streamed into Amazon Redshift, materialized on Amazon Redshift in a materialized view. Using the customer payment history, machine learning model was deployed onto Amazon Redshift as a user-defined function. This user-defined function was used using a SQL on the data, which was already streaming into Amazon Redshift, to identify whether the payment card transaction was fraudulent or not fraudulent. So this pattern, we have also seen customers adopting streaming ingestion, but also leveraging Redshift machine learning to do prediction. For customers who really require stringent fine-grained access control, or they have stringent security requirement, or need to support multi-tenancy, Amazon Redshift not only provides security at rest in transit, but also with role-based access control, it provides the customer the ability to implement fine-grained access control, be it at column level, row level, or also implement dynamic data masking. If you are an existing Amazon Redshift customer or considering Amazon Redshift for your new workload, or you're evaluating your Amazon Redshift, we would love to get engaged with you. Please reach out to your account teams. To know about Amazon Redshift or the new features, please reference the resource link. We would love to get your feedback, and we would love to learn how you experienced this session, how your experience for this session was. Please fill out the survey. Thank you.